Thanks, Vivek. Hello, everybody. My name is Shankhachur Roy. I'm working at the University of Manchester for optimized cylindrical preform manufacturing. So the objective is to develop novel manufacturing technologies that are capable of producing cylindrical preforms with fiber orientations as desired by the optimization. So the optimized fiber lab will not be constrained by the conventional machine's limitation. In Manchester, we have commercially available equipment. As you can see on the left-hand side, we have a radial braider and then followed by a maple braider. Both of these braiding machines are two-dimensional braiding machines that produces single layer structures, and also a profile braider on the far right-hand side, which produces 3D structures. The 2D braiding machines produce a hollow cylindrical structure. So these are widely used for overbraiding purpose. On the other hand, the 3D braider produces a solid noodle-like structure that you can see on the right-hand side of the slide. Although 3D preform has advantages, as all my colleagues have previously mentioned, 3D profile braiders are not suitable for overbraiding onto a core. So as part of our development to overcome these limitations, in stage 1, we developed a multi-axis filament winding equipment that produces a cross-wound structure, which is earlier mentioned as a quasi 3D structure, you can call it. And the equipment was commercialized by our industrial partners in Signet Texcam. In stage 2, we combined the multi-axial winding method with the capability of adding through thickness reinforcement. As you can see on the right-hand side computer tomography image, the binder is going through the wound preform, and we are further developing this technology at the moment. So alongside the development of, this is the one. Alongside the development of different technologies, we are producing a demonstrator pressure vessel with optimized architecture decided by Mikhail at Nottingham. So for this purpose, we made an inline braiding and winding process that is capable of producing quadriaxial preforms, optimized quadriaxial preform. So otherwise, we call it a braid winding method. You can see an early stage development of this pressure vessel, combining so the preform combines the advantages of both filament winding and braiding technology. So I'll conclude my presentation, and we will show you a video that will showcase some of the highlights of Manchester-Nottingham collaboration. Thank you.
Dry fiber reinforcements are often used to manufacture composite components. Most common, they consist of several layers of 2D fabrics which are simply stacked together. Alternatively, it is possible to use 3D fabrics, which consist of several layers already woven together. They provide near-net-shaped preforms and offer better mechanical properties because of additional through-thickness reinforcement. We have extended the conventional design space of 3D fabrics, and we were able to show that it is possible to achieve better mechanical properties than is currently possible with conventional 3D fabrics.
In order to overcome the limitations of the current jacquard weaving technologies, the University of Manchester team collaborated with the University of Nottingham team to develop complex robotic fiber placement, jacquard weaving and braiding technologies for unconstrained optimization.
For pressurized tubes, braiding can readily incorporate triaxial reinforcement. Combining with the hook reinforcement, we can achieve optimum layups. In Manchester, we developed a complex braid winding machine that significantly expands the process capability to develop quadriaxial layup. This unique machine overcomes the manufacturing challenges of creating optimized fiber architectures.
3D fiber preforming using the patented multi-wave robotic system that we developed in this project is almost like additive manufacturing or 3D printing. Now we can place fibers in any orientation, any thickness along with through thickness binders, mixing various types of fibers such as carbon, glass and ceramics. The platform technology of 3D manufacturing system we developed can be used in composites, technical textiles, and in biomedical applications. Currently, we are manufacturing a large car floor panel using the multi-axial preform with through thickness binders. We are looking for potential industrial partners in order to demonstrate this technology in real-life applications such as in electric cars, structural batteries, and in space structures.
So thank you to the speakers for the presentations. Please could the speakers now join the stage and we can see if we've got any outstanding questions to answer.
Well, I try to answer as many questions as I can in the questions panel, but I'll be happy to take any more if anyone wants.
Okay. Well, you're just typing a reply, I think, to WeTan.
No.
Oh, okay, on my screen it says that you're replying. Oh, I don't know where that came from. Okay, so I'll start with a question from Ruben Newell. Says, hi Vivek, I'm interested to know more about how yarn reduced damage was achieved even with an increased amount of weft insertions per shed. Can you give me more information on the typical weaving speeds and warp, weft, and binder yarn tensions used?
I mean, typically in a 3D weaving machine, like assemble a denier weaving machine, we put single weft. Let's an example, we got 10 layers. Every weft you need to change the shed, and when you open the shed, for every time you rub the fibers each other and create a lot of fiber damage. In the multi-weft system we developed at Manchester, we simultaneously open 22 sheds. So even though the machine is running really slow, the output is much higher than a conventional machine. And we even tried, we are actually weaving ceramic alumina fibers as well. It's very well in warp and weft directions, even in off-axis. With tensions, it depends on many factors. If it's a 12K, you can work with 70 gram tension on each toe, but it depends mainly on the fiber types. If you're taking 3K or 1K, you need to have much lower tensions.
Okay, thank you, Vivek. And actually, we have another question for you from WeTan. He says, thanks for the great presentation and videos. I wonder what is the mechanism for the 3D preform to keep the shape before the resin infusion? Will it collapse if the Z direction structure is too complex?
Is it for me or?
Yes, sorry. Yeah.
That's fine. If you remember in the process presentation, there is a I shape. We can because of the binder tensions, everything holds in place. It's a really rigid structure. It won't fall off. Normally in weaving, if you see a denier weaving, we cut every weft, but in our case we have a salvage, which means we lock every weft, so we don't cut the edges. If you cut an edge of a 3D fabric in the middle, the weft or the warp yarn start falling off, but we always lock it in place. That's one of the advantages, because normally if you infuse a sample using a 3D structure, depending on the technician, the fibers will take out the fibers from the edges, and that will change the mechanical properties. In our case, we lock every fibers in place.
Thank you, Vivek, for that answer. We have a question for Mikhail. It says, have you used multivariable control algorithm techniques for the optimization apart from the generic algorithm you presented?
Thanks for the question, Agnostus. No, we haven't used multivariable control algorithm. To be honest, I'm not that familiar with it. I'll have a look at it. We used some other optimization algorithm, or we tried to use some other optimization algorithm, and one of the problems that quite often they either converge to a local optimum or not that suitable for very nonlinear problems as we have here, because we have quite a lot of parameters, and say the binder pattern is not a continuous parameter, so it was a bit of a problem. Thank you.
Okay, thank you for that answer. I'm just scrolling down to see if there's any more, because I know you've answered a lot already. Now, Nick, are you replying to Dr. Claudio Barri on his recent question? You're on mute.
Yes, I am. Yeah, Claudio, we don't have any pultrusion activity in the hub at the moment, and maybe we should actually. But as it happens, the University of Nottingham is working on an Innovate UK project with industrial partners on pultrusion. So, I mean, we recognise that as an important element.
Okay, thank you for that. I'm just scrolling through. I think we more or less answered them all. And so do any of the speakers have any last minute comments to make, or anything further to any of the questions they've been asked? Would like to add anything?
Oh, there is an interesting question from Chris.
Mm-hmm.
Well, it was to Prasad, but I think all of us actually have something to say about it. Prasad, do you want to start maybe, or do you want
yes.
to start? So the question is how to actually model 3D woven structures and predict the performance of structures with non-constrained technologies. And I think that's actually the main challenge. If we want to model something, we don't know how it looks like. That's something which requires either a lot of insight. Sorry, I think Prasad disconnected. So it either requires a lot of insight, which means that we need to manufacture something ahead, do a micro-CT or a microscopy, and then model it later, or we kind of need to predict the structure using some sort of numerical algorithm. And there are, say, digital chain element methods and other things to model these 3D structures. So that's a challenge.
Yeah. Also, I mean, the weaving system, we advanced quite a lot. Now we can have tapers going up or down in the 3D structure, along with toe steering is possible as well. We even made some demonstrators. So it's all 3D weaving is becoming almost like additive manufacturing now. It's very close to it. So as long as the modeling can predict exactly what we need, manufacturing is catching up with that.
Sorry, my internet dropped off in between.
Yeah.
Would you like to add anything to that question, Prasad? Or
sorry, could you repeat the question?
Yes. So the question was, modeling is still an issue for 3D woven structures. How will we overcome and predict performance with non-constrained technologies?
I mean, as Mikhail explained, I mean, as we remove the constraints of manufacturing, it's bringing up all sorts of new unit cell geometries. And it's a matter of text gen to upgrade and accommodate much more flexible architectures, and also incorporate these new algorithms for optimization, I believe. I think optimization and manufacturing flexibility go hand in hand in progressing this technology.
And Louise and Mikhail are working very hard to do just that.
I think Prasad's connection lost again.
No, I'm here.
Oh, you're here. I'm here. Not
here.
Okay, well, we're out of time now, so let's close the webinar. So thank you to the speakers for your presentations. And thank you to everybody for joining us and for your interest and questions. If you would like to provide any feedback from today's session, then please do so by sending me an email. You can also contact the presenters directly if you'd like to follow up on any questions you asked. You can find contact details on our website, www.simcom.ac.uk. We hope you all enjoyed today's session. Bye for now.
Bye.